I will be switching screens quite a bit, so if you do have a question or something doesn't show up on the screen, sing out, and I want to make sure it gets up there for you. Okay, so the first thing we want to do is take a look at the used Honda example, and let's see, where is it? Well, that's not it. Okay. There we go. There it is, used Hondas, okay? And so we've talked about this the last couple of days, and I've asked you to look at some of these examples. So today what I'm going to do is I'm just going to literally walk you through it step by step. I will not create the scatter plot on paper. Obviously, I don't think you'll be asked to do that. I think you'll be asked to interpret one if you're asked about this. And so, but I will do a little calculator work here just to refresh your memory on using the calculator to enter this data. Again, no way they'll ask you to do it because it's a 4-function calculator test, but it is good to kind of see how this works, and maybe you can use it to your advantage. Okay, so let me pull up the calculator, and I have already entered the miles driven in thousands of miles in L1 and the miles driven in L2. So now what we can do is we can go to stat and then calculate. And if you select 2 variable stats, it will calculate the statistics for L1 and L2 at the same time. You can do it one at a time. It just is a little bit quicker this way. And so when I hit calculate, we get X bar is 50.45 and SX is 19.27. So I'm going to go ahead and write this down. X bar equals 50, and you'll see this in just a minute. 45 SX is 19.27. And you'll notice I'm carrying 4 significant digits here, just to be sure that when I do some intermediate calculations, I'm in good shape. Y bar is 14,426. Now that's to 6 significant digits, but I wanted to go ahead and carry it to the ones place, and SY is 18, and this is a crazy one. This is 1899. And I'm going to go ahead and carry it to 5 places too, just because I don't want to round that up to 1900, but it's pretty close to 1900 and we'd probably be okay. So that's two variable stats. That's how that works. And so on the calculator, it asks you to create the scatter plot. I'll just show you how to do that real quickly. Obviously, you cannot be asked to do this, but I'll show you how to do it. We'll turn stat plots number 1 on, and the type we want to select is the first one. We want to do a scatter plot of X is the explanatory variable and Y is the response, because the price is based on the miles driven. And so when we hit graph, we should see, let me do zoom 9 just to make sure we've got everything. And so we can see the data. And then if I hit the trace key, then you can see the first data point, X is 22 and Y is 17,998. And if I move over to the next data point, it's the next point down in the table, 29,000 miles driven and a price of 16,450. So you can see the scatter plot there. So what we're asked to do here is describe the mileage. And so now I'm just gonna start doing a little writing for you guys so you can follow along. And again, I will show you. I will send you my solution for this after we're done. So if you just want to follow along, that's fine. So we've got the scatter plot, the association. Remember the acronym, really not an acronym, but it is DF SO, and the direction is linear. I'm sorry. the direction is negative. The form is linear. It follows a pretty linear pattern. The strength is, if we go back and we look at the picture here, oops, I don't want that. Wrong calculator. This one, we can imagine a straight line, and would be pretty closely adherent to a straight line through there. So we're going to say it's moderately strong. I think you could even say it's strong. And then outliers, we would say there are no apparent outliers. There are no dots that are way over to the left or to the right, no dots that are way to the top or to the bottom. So we'll just say that there are none apparent in terms of outliers here. So no apparent outliers. So that's all we want to do. Now you probably want to write this in sentence form, and what we might say is the association between mileage and advertised price is a negative, linear, moderately strong association with no apparent outliers. Okay, so that's what you might write something like that. And I don't remember exactly what mine said, but you get the idea. But you want to make sure that you use these 4 checkpoints. You want to talk about all 4 of them. Okay. So now we want to identify the regression line for the data and interpret the slope and y-intercept in context. Okay, so now we'll go back to the calculator here. Tell you what, let me move this over a little bit, and then now. So when I if I want to calculate the regression line using the calculator, and again, I don't think you'll be asked to do this, but you will certainly be asked to understand how this works. So we'll go to calculate and scroll down to choice 8, and we want to do a linear regression, a plus bx. Now you notice choice 4 is ax plus b, and it gives you the same values. The problem is this is more like in the Algebra 1 format, where the constant a represents the slope, but typically in statistics textbook, the constant a represents the intercept, and the constant b represents the slope. So we're always going to pick 8. And again, our x value is going to be in L1, and our y values are in L2. And we're just going to go ahead and calculate that value. And so we get a regression line in the form of a plus bx, where a is 18,774, and B is negative 86.19. So I'm going to go ahead and just write that. But remember, we want to write our regression line in terms of y hat equals 18,774. And notice that B is negative. So I'm just going to go ahead and put the negative sign in there, 86.19. And then X. So there's the regression line right there. That's it. Now we want to interpret the slope. Well, the slope, let's just do this. B equals negative 86.19. And that means that the predicted price for a used Honda decreases by $86.19 for every 1,000 miles driven. Now, it's important that we recognize that this says every 1,000 miles, because our miles driven up here is in thousands. So if you had said for every mile driven, you might have a point taken off there, because always keep track of the units for the X variable. So that's the interpretation of the slope. To interpret the y-intercept, A equals 18,774, and that is the predicted price for a vehicle with 0 miles driven. And if you had watched the other videos, or if you were in class the other day, I mentioned that sometimes the y-intercept has no practical meaning here. And so this is one of those cases. It's impossible to buy a used Honda with 0 miles driven. You might say the context of this means that this would be the expected price for a brand new Honda. That would probably be okay. But in the context of our question, where the explanatory variable is miles driven, we're just gonna keep it like this. And honestly, this is one of those where the y-intercept doesn't have a lot of practical meaning. Although, I mean, you could say it's for the price of a new one, but in the context of our question, we're only concerned about buying used cars. Okay, so the third question is predict the price for a car with 50,000 miles. Well, we're going to use our prediction equation. Y hat equals 18,774 minus 8619, and we're just going to plug in 50,000 here. But we're really not going to plug in 50,000. We're just going to plug in 50, because our X variable is in thousands of miles. So be very, very careful that you're plugging in a value that makes sense with the units for the explanatory variable. And if you do that arithmetic, you get Y hat, or the predicted price, is 14,464. Okay, so if you were to go to CarMax back in the day when this study was done, and find a car with 50,000 miles on it, you would expect to pay this price. Now, there's some variation in that. We're going to talk about that in just a minute. Anyway, that's the predicted price. Okay, so now the last question on the first page is, can you use this data to predict the price of a car with 250,000 miles driven. And yesterday we talked about this thing called extrapolation. And notice that the range of values for our data is from 22,000 to 86,000. And so 250,000 is well outside that range. And so our answer is going to be a big fat no there. And we're going to make sure we use the term. This is extrapolation. This value is far outside the range of data for our prediction line or prediction line, regression line, whatever you want to say. Any prediction outside the range is likely to be inaccurate. Okay, so that's what extrapolation is all about. It's plugging in a value well outside our useful range, and the results we get are inaccurate. We have no idea what the price of a used Honda CR-V with 250,000 miles is. Now, some of you who know what a Honda CR-V is and can imagine what it's going to look like after 250,000 miles, you will you'll kind of laugh to yourself about that. And in fact, if you plug this value in to this prediction equation, you'll get a negative number. And so, what that practically means is somebody would have to pay you to take it, essentially. That's what that means in context. Okay, so that's extrapolation. We're not going to get involved in extrapolation. Okay, so calculate the residuals in this case and sketch a residual plot. Well, again, my solution will show you how to use the calculator to sketch the residuals, but I'm really not going to do that here. I think it's more useful for us just to make use of this chart, and we'll create a column here that is y hat, and then we'll create another column that is the residual. And so what we're going to do is we're going to calculate y hat for a value of 22,000 miles. So what that means is we'll plug in 18,774 minus 86,19 times 22, and that's the predicted value at 22,000 miles. And so we'll just do that with our calculator here, just really quickly. And we can just type it in as we see it, 18,774 minus 86.19 times 22. So the predicted value is 16,878 rounded to the nearest dollar. So that's the predicted value. And the residual, remember, this is AP statistics, so the residual is always the actual minus the predicted. So the actual price is this minus the predicted. So we'll just type that in, 17,998 minus 16,878. And so the residual is $1,120. And so in context, what this means for us is that based on this data, our prediction model would suggest that the price of the Honda with 22,000 miles should be 16,878. and CarMax price was 17,998. And so what you might say that you are overpaying by $1,120. In other words, the residual is positive, so the actual price is above the predicted price. And so in context here, you might say that you're overpaying by $1,100. Okay, so let's just pick another one. Let's just go down here to 35,000, and so we'll do 18,774 minus 86.19 times 35, and we'll plug that in. 18,774 minus 86.19 times 35. I think that's right. And so that predicted price is 757. And so here the residual again is the actual minus the predicted. So this minus that. So 14,998 minus 15,757. And here the residual price is negative 759. So in this case, you would say, hey, I got a good deal. I paid less than my prediction line would have expected. And so, or negative residual in this context is, I got a pretty good deal. Okay, and you could go down through the rest. For the interest of time, we won't we won't go through that one. When you get my solution, it will show you a way to use other lists to calculate this column and this column all the way from top to bottom without doing the steps one by one. Again, I don't think that's a skill you're going to need for the test, so I'm not going to spend a lot of time on it. And so question 6, I think, is something that you may have to come up on. And it is calculate the slope and y-intercept using the means and standard deviations of the data. Okay, and so what that refers to is the formulas that are on the top of your formula page. Y hat equals a plus bx we've already looked at, but these two formulas right here allow us to calculate this prediction line just using the means and the standard deviations and this R value. Here's the equation for R. Not going to talk a lot about it. I don't think you need to know a whole lot about it. But the calculator calculated it for us already, and so we're just going to take advantage of that. Now, I recognize calculator calculated this value for us as well, but my guess is you might be given data that looks like this. You might be given this data, X bar and SX, and you might be given Y bar and SY, and you might be given R equals, and I don't remember what R equaled. So I didn't write it down. Shame on me. Calculate 8. R was equal to negative 0.8742. Okay, so I can kind of envision you being given this data right here in a box and told that it is computer generated data, and you're asked to calculate the regression line. I think you can do this with a 4-function calculator, and so that's what we'll do here, and we'll need these formulas. So the first formula is y bar equals A plus B times X bar, and we'll need the value of B is equal to R times SY over SX, okay? So looking at these equations here, I have all the values I need, but I need to calculate B in order to plug into here. And so I'm going to go ahead and calculate B. B is equal to R, and I said it was negative 0.84, nope, negative 0.8742 times SY over SX, and that's 1899.6 over SX 19.27. And so let's do that with the calculator. So negative 0.8742 times 1899.6 divided by 19.27. Again, this is all four function calculator stuff, so I think this is something you could be asked to do, and it turns out B equals negative 86.18. And when we calculated it with the calculator, we got 86.19, negative 86.19. And so with a little bit of round off, we're not going to be too worried about that. But please note that if I had not carried these to at least 4 significant digits, then I might have been off somewhere up here instead of on this very last digit. So when you're doing these calculations, make sure you carry plenty of significant digits. Okay, and so now I have B, and Y hat is in the form of A plus BX. So I got to calculate A, but I've got to rearrange this so that A, all I'm going to do is subtract BX from both sides. A is Y minus B times X bar. Now I can plug in for A, and I said Y bar was 14,426 minus, now minus a minus is a plus, 86.18 times X bar, which was 50.45. And just to refresh your memory, those values came from just doing 2 variable stats on L1 and L2 there. And so now when I calculate that, 14,426 plus 86.18 times 50.45. And we get A is equal to 18,773. Well, 18,774, we'll call it. And if we look back, that's exactly to 5 decimal places what we got before. And so now we would say Y hat is equal to A, which is 18,774, plus BX, and B is a negative. So I'm just going to go ahead and write negative 86.18 times X, and your reader will give you full credit for that, 100%. And we'll go from there. Okay. So question 7 involves, the way I've set this particular problem up involves a great deal of calculation, which I don't think you'll do. But I do want to talk to you about what this prediction error is. And I'll show you, I'll set up the formula here. It's not on your formula sheet, so there's no way you'll be required to know it. And you couldn't calculate it even if you wanted to. But the prediction error S, because we've talked about prediction error, or we've talked about standard error in our models before when we did confidence intervals. And so this prediction error is similar to that, but the formula it's pretty nasty. It's the sum of the residual squared divided by n minus 2. And if you do all of those things, and you'll see in my solution, I give you the values and all of that. And that value is $972 when you go through the calculations. Now, you might be asked to interpret what is, given this value, given S is $972, what does this mean? And so this is what I want you to recognize. The prediction error is the amount that the model or the prediction line is expected to be off for any particular value of X. In other words, it's almost like a confidence interval. If you remember our graph, it was, I don't know, it was something like that. It was negative. And so if we had plotted the line, the regression equation would have looked something like that. Well, the prediction error says that for any particular value of X, that there is a range of values, $972 above and below, that are reasonable for this thing. So if, like before, over here, when I calculated the residual, that residual of $1,120 is greater than my prediction error. And so I would look at this and say, this is a bad deal. I'm not buying that car at that price. If I can talk CarMax down a little bit, then I'll take it. But the prediction error says it should be this plus or minus that $972. And anything in that band, we're going to say is reasonable. Or when we talked about confidence intervals, we said that these were reasonable values or plausible values for p hat or x bar. Well, what this prediction error tells you is that anything between here and here for this price of the car, whatever that X1 value is, anywhere in this band or in this interval is a plausible price for the car. And so if it's in there, then you say, okay, you might want to haggle a little bit if it's too high. But if you don't get much out of it, then you can say, all right, at least I'm within the prediction error and I'll go on. So formally, what this means, let me just go ahead and write it, and you'll see this when I send you my solution. When using number of miles driven to estimate the price, we will be off by an average of $972. Okay, and so this prediction error again is it's similar to a confidence interval around this particular value. And so any price between here and here, we would say, is a plausible or reasonable price for that number of miles driven. Okay. That one is, that takes care of the used Hondas analysis. And honestly, if you can handle anything on these pages, I think you're going to be in pretty good shape. Now, what I want to do, I sent you guys this um, set of questions. There are 3 open response questions in the document I sent you before class, and this is the 3rd one. And the reason I want to talk through this one in class is because I think this is pretty likely what you're going to see on the test in this topic. Okay, so what I expect is you'll be given a scatter plot with an X value, and then in the context, this is, I won't read it word for word, but basically the more wildebeest in a particular area, the more acres of fire are going to be burned, and or less. It is crap. I've got my wrong glasses. Let me see. This is, yeah, thousands of wildebeest % burned. Okay, so the more wildebeest in an area, the lower the percentage of burn. The fewer, the higher percentage of burn. And so that's the data. And so I think first question would be describe the association between wildebeest and % of land area burned. And so again, we're going to say the direction is negative. The form is linear. It looks like a linear model would fit. And it is reasonably strong. The dots all fit within a fairly narrow band, moderately strong. And we'll see from this data here how strong that is. Moderately strong, negative, linear, moderately strong, correlation or association. And then we have to talk about outliers, and we might say something about this one here. If I were to draw the line, this guy here might stand off pretty far from the line. And so, but I really don't know. So I might just say, to be careful, I might say with a possible outlier. Okay. But again, I haven't done any calculations. I'm just looking at this. And then, and so now we're asked to give the equation of the least squares regression line. Well, here is Minitab output. And of course, you don't have to do any calculation with your calculator here. But you do need to be able to read, and what you're going to be looking at is the column labeled coefficient, and the horizontal row here. One of them is labeled constant, and one of them is labeled wildebeest. Okay, in thousands, and so this is clearly the X variable. Okay, and so the constant that goes, or the coefficient that goes with the X variable, is the slope, or B. The constant value is the y-intercept. So I'm going to take this data here, and I'm going to say my regression line is y hat equals A plus BX, and A in this case is equal to this, 92.29. And B is equal to negative 0.05762. And so when I write the regression line, and notice it says define the variables. Okay. I've defined the constants. I haven't defined the variables. So I want to say X is defined as the population of wildebeest, and that's in thousands, and Y is defined as the % of area burned, and that should be good enough for our definition. But you want to make sure you get X and Y included here. These are the variables. A and B are constants, so just writing them down isn't defining any variables. So you want to make sure you get X and Y. So now we can say Y hat is A plus BX 92.29 minus 0.05762 times X. Okay, and so that gets our equation defined. We define the variables, so the reader knows that we know exactly what's going on here. So now we want to explain the slope of the regression line and what it means in this setting. Well, what it means in this particular case is that for every increase of 1,000 wildebeest, the percent of area goes down by this much. The percent of area goes down by that much. So for every 1,000 increase in wildebeest, the percent of area burned goes down by about 0.05. You could even say 0.58 here, but to be precise, you could even convert this to a percent. It goes down by about 5.8%. Okay, that's a little bit more readable, but that's precise. You'll get full credit. Find the correlation. Okay, so the correlation we talked about earlier is a value of R, and it's going to be between -1 and 1. We expect it to be negative. But when I look at the data, when I look at this data box here, I don't see an R, but I do see something called R². And so if I know that R², and I need to convert this to a decimal, is 0.646, then I can take the square root. Then that implies that R is equal to the square root of 0.646. And let me do the calculator here, second function. 0.646, 0.8037. Now there's a real danger here, because what I just did, when you take the square root of both sides, then you have to consider that this is plus or minus that, right? It's from Algebra 2. And we know that the slope of this guy has got to be negative, so I want the negative value here. So R is equal to negative 0.0837. And interpret this in context, okay? So this value is close to -1, indicating, now I can even take this moderately strong off here, indicating a strong association between wildebeest population and percent area burned. Okay. And then the last question is a linear model appropriate for describing the relationship between wildebeest and present? And so that's where this residual plot. This is a plot of residuals versus wildebeest. And really all it does is it takes this value. Let's imagine, I'm just going to sketch in a line. And then so what it does is it takes this value, calculates the residual, the actual minus the predicted, and it's a positive number, so it's up here. The next one, the actual, well, this one is negative, and this one is positive, this one's negative. And you can kind of see that pattern here, positive, negative, etc. So all I'm doing is I'm taking this data, and I'm kind of really just taking this line and plotting it horizontally. But what I'm really looking for is if a linear model is appropriate, then this pattern is going to be random. This pattern of data here is random. In one of the other classes we had the other day, there was a very definite parabolic shape in the residuals. And so this one is random. And so what that says, that's a good thing. Random is good because that tells us that a linear model is appropriate. Okay, so one of the things we might say here is, since the residual plot is fairly random, or we might say has no apparent pattern, anything like that, no apparent pattern, then a linear model is reasonable. For this relationship. Okay. And so that's it. I really do anticipate if you get a question that requires you to talk about regression, I expect that you'll get the scatter plot, you'll probably get the residuals, and you'll get a box of data. And what you need to know is all of these things. Now, the S, the predicted, prediction error, that's this guy here. This S value is the prediction error, and what that says is that on average, the actual value will differ from the predictive value by about 16% burned. Okay, so again, that kind of provides this confidence interval that goes along with our graph here. Okay, so the very last thing, and I know we've been going for almost an hour, but the very last thing I want to talk to you about is the meaning of R-squared. And you might be asked about R-squared. And so I want to put this up, and I'll send you this page. Actually, I'll send you this page to remember to just go read this paragraph in your textbook. R-squared is the R value, the correlation factor squared. It's always a positive value, of course, and it's always a value between 0 and 1. And it talks about the fraction of the variation in values of y that is accounted for by the least square regression of y on x. In other words, if R-squared is high, then most of the variation is accounted for by the regression that we did. No other additional regression is needed. But if R-squared is low, close to 0, then there are other variables that might account for variation that we see in the values. And so let's go back to the wildebeest example, wherever it is, right here. Did I just, I did, I just deleted it. But so R-squared is 64.6. And so what that says is, and you'll get this in just a minute, since R squared is high, the least square regression line explains about 64.6% of the variation, not percent of the data, but variation in the area burned. So about 35% must be explained by some other variable. So a value like R squared of 66.4, 64.6, that's a big number. And so to find out where this other 35% is, we might go looking for other variables. And this goes back to our discussion when we did studies and surveys about hidden variables. There might be some other population like zebras that are grazing in the same land, or the soil content or the amount of rainfall in a particular year. There's some other variable that's kind of lurking in the background that accounts for about a third of the data, but about 2/3 of the data are accounted for by just the population of wildebeest. And so this regression is pretty strong, and it is you can see that because the dots are pretty close to the line. So again, go back and refresh, or go back and read that paragraph in the textbook about what R squared is, and you'll be fine. Okay, so I have kept you way too long. Thank you for staying with me. I see somebody didn't stay with me, but we won't mention it, any names. So for practice tomorrow, and after tomorrow, I'll be done talking about regression. There are two more problems on this thing that I sent you before. Go ahead and look at them, and we'll talk briefly about them, and we'll go from there. So here's what I need. I'll post this as a question in class. We've got about a week before your test. I want to use this time as wisely as I can. I have some review questions in mind for us to talk about. But if there is a particular topic, when you flip through the chapters in your book, if there's a particular topic in there that you want me to focus on, you want me to review a little bit more closely, then send me a message on Classroom or an email or something, and I'll pick out some questions that address that. But if not, I will pick out, or have picked out, some other questions that I think are in a format you're likely to see. They're not very calculator intensive, and therefore I think they're likely a likely format for you. Okay, so again, thanks for being patient. Thank you for your attention. Any questions before we sign off? We all good? Okay. All right, gang, you're awesome. I so wish we were together right now. I do. Hang in there. I'm confident you're going to do well on this test. I really am. I'm here to help you. So anything you need, you just let me know. Okay. All right. Well, we'll see you tomorrow. Y'all have a